I showed you how to solve this system by hand. We got lucky here because we had a way to cancel out the coupling right away so that we really didn't have to do a lot of algebra on this. It was more just applying the Laplace to these individually like we did before. And then we applied the Laplace, we solved for big X, big Y, applied the Laplace inverse, did some manipulation by looking at the form that resembled the most what we had inside the Laplace here. And we didn't even need to use partial fractions because they already came in forms that were invertible. And we got our 2 answer. And surprisingly, I didn't make any sign mistakes. But now I want to show you how to do it in Matlab, just in case, I had made a sign mistake and I wanted to double check. So let's go over here. Let me clear all the outputs and let me give you a little bit more space here. And let's say that this is a new problem. This is still chapter 4.6, exercise 9. So the first thing I'm going to do is I'm going to clear all variables. Clear all because I don't want to use the old variables. And then I'm going to declare new variables, and I'm going to declare that with the sims command, and it's going to be the variable t, the variable s. And I think I want to show you how we would have done it if we had a huge system. So let's say we have small x and y as well, and we have that x is a function of time and y is a function of time. So now I'm going to solve for x and y. And how am I going to do that? Well, one way I could do it is I could say I could input the whole system. So the derivative of x with respect to t, the second derivative, this specifies that this is the second derivative, plus the same command but for the y, and it's important to put y of t, otherwise it doesn't realize that this is a function, it'll give you an output of 0. And from this, I know that that was equal to t squared, and then I had the second one, which was similar to this. We had x double prime, y double prime, but they were subtracted, and that is equal to 4 times t. So now that we have these two, we can put them into the solve command here and say that we want to solve for x and y. And we want to redefine then x and y. So right here, what do we get? We get some errors here. And I think the error comes from the fact that he wants you to not define these this way. So, well, we tried. Let's stick with the method of applying the Laplace first by hand, and then we had our big X and our big Y. So had our big X and our big Y, and we want to solve for big X and big Y. So what are we going to do? Well, let's input the two equalities that we got. We got an s squared times the big X minus 8 times s, and all of that is equal to 1 over s to the third. Well, that's not, yep, 1 over s to the third plus 2 over s squared plus 2 over s squared. That was the first inequality. Sorry, the first equality. The second one, we got the similar thing here. No, we got an s squared times y, big Y, and that is equal to 1 over s to the third. 1 over s to the third minus 2 over s squared. Okay, so now I can put these into the solve function. So right here, I'm going to put solve. I'm going to say I want to solve for my big X and my big Y. I want it to output, so I won't put a semicolon. And I basically want to rename my big X and my big Y. And I do all of that, and I press Control Enter. And I see what it outputs. And it should output the same thing that we had. And once we have this, I'm gonna apply the inverse Laplace, or if you were on a test, first you apply the partial fractions. In this one, you really don't need to, but if you were to have to do that because it's an expression that's worse than this, then you would use the part frac command, and you'd put your X and then rename your big X. And same for the Y, you just change this to Y. And then you'd apply the Laplace inverse to the partial fraction version, and hopefully you can pick out the single transformations that Matlab did, and you can write them on your paper. So I Laplace would be a big X. That would be our small x of t, and y of t is going to be our I Laplace of y. And then we press Control Enter, and we try and see what we get. We got the same thing as before, but if you weren't sure, we would check the solution by applying it back into our two differential equations. So we have the derivative of x with respect to t, but not the first one, the second derivative, plus the same command but applied to the y, plus the second derivative of y with respect to t, should be equal to what? To t squared. Let's see, Control Enter. If the first one's true, you got a high probability. The second one's true. We get an equality here. So we get that this is indeed a solution. If we also want to check the second one, since it was similar, I'm going to do this. They were subtracted here, and here we had a 4 times t. And if you want to check that one as well, you can go ahead and press Control Enter. It's going to output. You get the same thing on the left and on the right. So you're sure that you got the right answer. All right, I hope this was useful, and I'll see you next time for perhaps a model that then we'll solve with Laplace. We'll see you there.